In this lesson, we're going to use very simple scatter plots and linear regression to do some rudimentary root cause analysis. Our starting point is some engineering data around the compressive strength of concrete. Someone went out and ran a whole bunch of experiments where they varied certain things in the mix of concrete and then measured the strength of the concrete by squeezing it until it broke. And they wrote down the compressive strength. Now, the interesting thing about this data is that all the variables, with one small exception, are continuous. That is, they're real numbers, and that lends itself to plotting the data in a two-dimensional space. Now, by convention, we typically put the predictor or the explanatory or the independent variable on the x-axis. In this case, it's fly ash, and we put the response variable or the dependent variable on the y vertical axis. In this case, it's the strength of the concrete. And the reason we plot this data is to look at it and get a rough sense for how it's shaped, what kind of relationship between fly ash and concrete. Could be positively linear, could be negatively linear, it could be completely nonlinear. That is why we plot our data first before we do any further analysis. In this lesson, I'm going to use Microsoft Excel to create a scatter plot, and the scatter plot is going to show me the relationship between fly ash and the strength of the concrete. So creating a scatter plot in Excel is a bit of a pain because you have to select very carefully. So I'm just going to hold down the Control key and select two ranges and then insert. Now notice there's two types of charts that seem promising. One is the line chart and one is the scatter chart. The line chart, it turns out, doesn't give us what we want at all, because the reason is the line chart takes the x values and treats them just as if they were just spacings. It doesn't realize it's a number and that it has a different interval. To explain this a little better, maybe I'll show you what happens if we hit the scatter plot version. So I go insert and I hit scatter instead and just pick the points. There I get a very simple scatter plot that shows me a cloud of data points, but on the x-axis I have the amount of fly ash, and on the vertical axis I have the strength of the concrete, and each dot represents a trial or a data point in my experiment. Now, what I like to do once I have a scatter plot is to select Design and make sure I move the chart onto its own sheet, which I'll call scatter plot. And that's the way it's quite a bit larger. Then I should do the layout and make sure I have my axes. So for example, on the x-axis I should have fly ash, and on the other axis I should have compressive strength of the concrete. And I'll leave that for you as an exercise. One of the reasons that we plot our data using scatter plots is not only to identify relationships between variables, but look for data problems. So for example, in this case, I have quite a few values of fly ash that correspond to 0. So the question is, what do these mean? It could mean that 0 fly ash was put in the mixture, which could make some sense in some contexts. Or it could mean, I don't know, or it could mean the operator forgot to enter a value, or it could mean when the data was exported to Excel, that piece of data wasn't transferred properly. There's a million different reasons you could have a 0 in your data. It's your job to find out what the source is. Given the way the fly ash cloud looks in this scatter plot, I'm thinking that the 0 corresponds to some kind of mistake. Excel has a feature that allows you to create a very quick and easy regression line on your data points once you've created a scatter plot. All you do is right click on your data points and look for add a trend line. So if I click on that, the first thing you'll see is there's quite a few choices, a lot of different types of trend lines. Some are linear and some, especially the polynomial, are decidedly nonlinear. Generally in business, we're only interested in linear relationships. It's very hard to wrap our heads around nonlinear relationships except in very specific circumstances. So you select linear, and then at the bottom, ignore the intercept, but decide to show the equation of this line on the chart, and also show this r squared value on the chart, and we'll see what we get. So it starts off, we get a very small equation, so I typically make that a little bit bigger and move it out of the way. So what this tells us is we have a line that's very special. It's the best fit line. It's the line that minimizes the errors between the line and that cloud of data points. So putting aside for a moment that this isn't a very good line, that is, it doesn't fit the data points very well, it fits them better than any other line. That's what that's what Excel does for us. The equation of this line is compressive strength equals 0.044 times x. Now remember, x is fly ash. X is the amount of fly ash we put in the mixture, plus some intercept. And typically in business, especially when we're doing root cause analysis, we don't care at all about the intercept. We need it if we want to do what I just did and predict a value of compressive strength given an amount of fly ash. But what we're really most interested in at this point is this coefficient, or this slope of the line. The slope, if you recall from grade 9, is rise over run. What this means is that for every unit increase in fly ash, we should expect to see a 0.044 unit increase in compressive strength. That coefficient, or sometimes called a parameter on x, is absolutely the most critical number. Now before we go and report this number to our boss though, we should look at this second number, this r squared, or coefficient of determination, or the way I think about it is explained variance. If you think about this line as a predictive model, it's not a very good predictive model. It turns out it's only explaining some of the variation we see in compressive strength as a function of variation in fly ash. That is, compressive strength still jumping all over the place off our line, even though there might be some relationship between fly ash and compressive strength. So r squared gives us the explained variance. It tells us that our model is explaining about 16.52% of the variability in our response variable.